which is equated to 0. Now see this f. We are taking the moment over a over here. So f into 0, it is 0. So we are not using the f, or we are not writing the f in this particular equation. So the same equations we have seen in the PPT. Please refer the PPT. So if you are referring the PPT, the equations that we got it right now is this one, m minus m plus delta m. Now if we are simplifying this equation, and if we take this negative term on the other side, we are obtaining this equation. We are obtaining these equations, and once again we simplify this one, then we achieve delta m is equal to w into delta x square by 2 plus f into delta x plus delta f into delta x. Now delta x and delta f, as the additional word is delta, are very small. Hence we can neglect the term delta x square by 2. Also, even this term, multiplication of two different delta f and delta x, are also smaller. So we are neglecting these small terms, and we can achieve an equation f delta x is equal to delta m. And if limit delta x stands to 0, we can achieve an equation dm by dx is equal to f. Very good equations we have been achieved over here. So basic significance is that the rate of change of bending moment at any section is equal to the shear force at that section. Or we can say that the slope of the moment diagram at a given point is the shear force at that section. So dm by dx is equal to f means the slope of the bending moment at a given section is the shear force at that corresponding section. So let us, if this dm by dx is equal to 0, means the slope of the moment diagram is 0, shear force is 0, means the bending moment m will be maximum. That is the point at which the shear force changes its sign from positive to negative or negative to positive. At that point, the bending moment value is maximum, and this point is known as maximum bending moment, as well as the point is called maximum bending moment point or contra shear point. Please don't combine the two words, point of contraflexure and contra shear point. Let us be revised. What is contra shear point? Contra shear point is a point at which the shear force changing its sign positive to negative or negative to positive, while point of contraflexure is the point at which bending moment changes its sign from positive to negative or negative to positive. So I wish you have understood very clearly this relationship between loading, shear force as well as bending moment. Let us proceed further ahead. Before we go ahead, it is to be remembered for a student that some of the textbook may use an equation df by dx is equal to plus w. What we achieve? We achieve df by dx is equal to minus w. Also, some of the textbooks are referring an equation dm by dx is equal to minus f, but we have achieved dm by dx is equal to plus f, provided there is consistency with the signs, and the same answers will be obtained. So the relationship, if we summarize in the short term, W, that is the force variable in terms of x, is equal to the load function, then Vx is equal to the integration of Wx dx, while bending moment Mx is equal to integration of Vx dx. Now let us summarize the full chapter that we had been studied up till now, since from series 1, 2 and 3, and let us be understood the concept, the relationship between the shear force and the bending moment with the load which is acting. Now let us revise. For a simply supported beam, if subjected to a point load, then the shear force which is remaining constant, means between 2 point load, the shear force which acting as a constant, means shear force changes by horizontal straight line. Another observation, at a point load the shear force changes suddenly, while for bending moment between 2 point load there is no load, then bending moment variation is given by inclined straight line, which is shown over here clearly. Now for another kind of beam is same, simply supported beam, but the load goes changes, that is uniformly distributed load, which is distributed equally along the length of the beam. Then for shear force which is changes by inclined straight line, so shear force over which is shown over here, which is changes or shown, which is inclined straight line, while the bending moment variation is given by parabola. So for a UDL, bending moment variation is given by parabolic nature, while for a beam which is subjected to uniformly varying load, the load which is uniformly changing along the length of the beam, then the shear force variation is given by parabolic nature, while the bending moment variation is given by cubic parabola. So this basic things that we had been studied till now previous case. Now next one, for a beam subjected to a moment or a couple at a particular point, then there is not a single effect on the shear force diagram at that particular point. I will revise the statement once again. For a beam subjected to a moment or a couple at a particular point, definitely it affects on the reaction. It changes the value of reaction, but there is no effect at that particular point on the shear force diagram. While for a bending moment, when there is a moment or a couple which is acting at a particular point, the bending moment changes suddenly at that particular point or section. Next, for a cantilever beam. So before we proceed further for a cantilever beam, then it has been remembered from the previous slide that bending moment nature shown is sagging throughout. So for a simply supported beam with any kind of loading, then the variation of BMD are of the nature of sagging nature. Now for a cantilever beam, please visualize that the bending moment nature is of hogging type of nature. Otherwise, the rules are remain same. For a point load, sudden change will be there on shear force diagram, while between 2 point load there is no force. The bending moment variation is given by inclined straight line. Similarly, for the UDL case, shear force variation is by inclined straight line, while bending moment variation is given by parabolic nature. So, let us be understood the sum of the properties of shear and the bending moment that had been studied in the previous lecture. The area of the shear force diagram to the left or right of the section is equal to the moment at that section. We had solved one numerical based on this also. Second observation, the slope of the moment diagram at a given point is the shear force at that particular point. Third observation, the slope of the shear diagram at a given point equals to the load at that particular point or section. Next observation, the maximum moment occurs at the point of zero shear that we have derived from the equation. When the shear diagram is increasing, the moment diagram is concave upward. Very interesting observation. When the shear force diagram is increasing nature, the bending moment diagram is of concave upward. Next, when the shear diagram is decreasing, the bending moment diagram is a concave downward. Now, so up till now we have studied about the shear force and the bending moment with respect to the different kinds of loading and three different kinds of the beams: simply supported beam, cantilever beam and overhanging beam. We have plotted so many kinds of diagrams for shear force and bending moment with variety kinds of the loading. Now we are going ahead with the bending stress. So the question may arise in our mind, what is stress? Before we proceed further for bending stress, it is at most important to know that stress, what is stress? Stress is the ratio of force by cross-sectional area. What is force? Force is the force of resistance. So normally the stress is defined as the force of resistance divided by the cross-sectional area. We are discussing right now about the bending stress. So if we take any section of a beam and consider the free body diagram on either side, maybe of left or right, we find that there must be the three internal stress resultant at the section in general to maintain the equilibrium of the free body diagram. What are those three? Please we recall. The first is the horizontal, second is the vertical and third is the moment. In technical words, these three are referred as bending moment, shear force and axial force. So for any kind of beam, when it is subjected to the external loading and if we cut a section, then at that section the three internal forces are acting, namely called shear force, axial force and bending moment. So these internal stress resultants are equal and opposite to the external effects of the load on the section. So here we are discussing the effect of bending. So let us discuss the effect of bending. Please refer this. Here the beam, simply supported beam with external loading which has been given to us, maybe in terms of the point load, uniformly varying load, maybe in terms of a couple. Let us take a section XX over here and take a section left part over here. Then at the section, the three different internal forces are acting: horizontal force, vertical force, and the moment. These three internal forces are developed. Now if we take the effect of the bending moment, which is shown over here. So what is this figure? This figure shows the cross section, that is the third dimensional figure over here. So this moment create or generate a forces in terms of the compressive stress and the tensile stress. This stress development is referred as the bending stresses. Precisely, if you go ahead, under the effect of the lateral loads, the beam bends and longitudinal axis takes curved shape. The beam produces an internal resisting couple to balance the bending moment due to the applied load. This couple is generated by normal compressive and tensile forces in the section that we had been seen over here in the previous slide. Please refer. Because of the external loading acting on a beam, my beam bends. And because of the generation of bending moment, to resist this bending, the compressive force and the tensile force are developed at that particular section, the section that we have taken care over here. Please refer this particular figure. So any kind of the external load which is acting on a beam, then please refer this one. In terms of the compressive force and tensile forces are developed in the fibers of a beam. So in the top zone, if you are referring compressive forces, and in the bottom fibers